Welcome to this lecture on geothermal reservoirs, physics, simulation, monitoring, and digital twins. In this video, I want to show that geothermal energy is not only about drilling deep wells. It is about understanding how heat, water, rock, fractures, and operations interact underground. Reservoir simulation gives us a scientific way to see the invisible subsurface and to make better decisions before expensive field operations begin. Today, we will build the story step by step. First, the reservoir concept. Second, the governing physics. Third, the numerical simulation workflow. And finally, how AI and digital twins can support safer and more sustainable geothermal development. Here is the learning journey for this video. We begin with the conceptual reservoir, where heat, water, rock, and wells interact. Then we move to the governing physics, including mass balance, Darcy flow, heat transport, phase behavior, and stress. After that, we build the simulator, data, static model, grid, wells, calibration, and uncertainty. Finally, we discuss the future, monitoring, AI-assisted simulation, and the geothermal digital twin. My goal is that by the end of this lecture, you can explain not only what a geothermal reservoir is, but also how to model it and how to manage it responsibly. Why does geothermal reservoir engineering matter now? Because geothermal energy can provide stable, low-carbon heat and electricity, but the subsurface system is complex. The slide shows that global installed geothermal power capacity is still relatively small compared with the technical potential of deep geothermal resources. This gap is the opportunity. To unlock it, we need more than drilling technology. We need reservoir engineering, reliable temperature forecasts, pressure management, induced seismicity control, and long-term sustainability assessment. Simulation is the bridge between geological uncertainty and operational decisions. It helps us ask, where should we drill, how fast should we inject, and how long can the reservoir maintain useful heat? A geothermal reservoir can be understood as a natural heat engine. At depth, the Earth provides the heat source. That heat may come from magmatic systems, hot basement rocks, or simply an elevated geothermal gradient. The second element is the fluid pathway, natural fractures, faults, porous formations, or engineered fracture networks. The third element is circulation. Cooler water moves downward or is injected, absorbs heat from the rock, and returns to the surface as hot water or steam. The key point is simple but powerful. Geothermal energy is not stored only in water. Most of the thermal energy is stored in the rock, and water is the carrier that brings this heat to the surface. This slide summarizes the dynamic of a geothermal reservoir. First is heat, the geothermal gradient, heat flux, and thermal recharge rate. Second is storage, porosity, fracture aperture, connected volume, and the amount of hot rock contacted by the fluid. Third is permeability. Without connected flow paths, heat cannot be produced economically. Fourth is chemistry and integrity. Minerals can precipitate or dissolve, wells can scale, and stress changes can alter fractures. When we model a geothermal reservoir, we are not just modeling one property. We are modeling an interacting system. A good simulation must therefore respect thermal, hydraulic, mechanical, and sometimes chemical processes. Now we enter part 1. From geological setting to reservoir concept. Before we write equations or run a simulator, we need a mental model of the subsurface. Where's the heat? Where's the water? Which fractures are connected? Where are the safe locations for injection and production wells? A numerical model without a strong conceptual model can look sophisticated, but it may still be wrong. So in this part, we build the geological and reservoir picture first. This is the foundation for everything that follows in geothermal reservoir simulation. Temperature gradient is the first control on geothermal potential. In the simplest form, temperature increases with depth according to the geothermal gradient. If the gradient is high, we can reach useful temperatures at shallower depth, which reduces drilling cost and risk. If the gradient is low, deeper wells may be necessary. However, gradient alone is not enough. A hot rock with no permeability may be technically interesting but difficult to produce. That is why geothermal evaluation must combine temperature, depth, permeability, fluid availability, and surface demand. The temperature profile gives us the first clue, but the reservoir engineer must still ask whether heat can be produced at a useful rate. There are several types of geothermal reservoirs. Natural hydrothermal systems already contain hot water or steam and connected permeability. These are the most straightforward resources when the geology is favorable. Enhanced geothermal systems, or EGS, are different. In EGS, the rock may be hot, but the permeability is insufficient, so controlled injection is used to create or reopen flow pathways. There are also sedimentary basin geothermal systems, which may be suitable for direct heat applications such as district heating. Each type requires a different modeling strategy. For a hydrothermal reservoir, we focus on existing flow paths. For EGS, we must also model stimulation, fracture connectivity, and induced seismicity risk. The production injection doublet is the basic geothermal circuit. Cold or cooler water is injected into the reservoir through the injection well. As it moves through hot rock, it gains heat. Then the heated fluid is produced through the production well and used at the surface for electricity generation or direct heating. After heat extraction, the cooled water is usually re-injected to maintain pressure and support sustainability. This sounds simple, but the details are challenging. If the wells are too close, or if a high permeability fracture connects them directly, the cold front may arrive too early. If the wells are too far apart, circulation may require excessive pumping. Simulation helps us design the balance. Before numerical modeling, we must define the conceptual model. This includes geology, faults, facies, fractures, thermal field, pressure regime, and boundary support. We also define operational assumptions, such as injection rate, production pressure, and reinjection temperature. The conceptual model is where expert judgment enters the workflow. It tells the simulator what is physically plausible. For example, a fracture corridor may create fast flow. A sealing fault may compartmentalize pressure. A deep heat source may recharge the system over long time scales. If the conceptual model is weak, even the best numerical method will produce uncertain or misleading predictions. Now we move to part 2, the physics of geothermal reservoirs. The conceptual model tells us what the system looks like. The physics tells us how the system evolves. In geothermal reservoirs, we need at least 3 major pieces: mass conservation, fluid flow, and energy conservation. In many cases, we also need phase behavior, geomechanics, and geochemistry. This is why geothermal reservoir simulation is such an excellent teaching example. It is a real multi-physics problem with direct practical consequences. Every equation has an operational meaning, and every modeling assumption affects the decision we make in the field. Mass conservation is the first governing equation. It says that the change in fluid mass stored in a reservoir volume plus the net flow leaving that volume must equal the sources or sinks, such as injection and production wells. In geothermal systems, density is not constant. It depends on pressure and temperature, and in two-phase systems it also depends on steam saturation. This equation explains why pressure is such an important signal. When we inject, pressure changes propagate through the reservoir. When we produce, pressure declines. By matching pressure data, we can infer storage capacity, permeability connectivity, and boundary support. Darcy flow describes how fluid moves through porous rock or fractures. Velocity increases with permeability and pressure gradient, and decreases with viscosity. In geothermal reservoirs, permeability is often the most uncertain and most important property. High permeability improves injectivity and production, but it can also create fast channels that cause thermal short-circuiting. Low permeability may protect heat storage but restrict circulation. Anisotropy also matters. If permeability is much higher in one direction, the cold front may move preferentially toward the producer. This is why permeability models, fracture characterization, and tracer tests are central to geothermal reservoir engineering. Energy conservation is the heart of geothermal simulation. The reservoir stores heat in both rock and fluid. Flow carries heat by advection, while temperature gradients move heat by conduction. Wells add or remove energy through injection and production. A good geothermal simulator must capture all of these terms. If we ignore advection, we cannot model thermal breakthrough. If we ignore conduction, we miss heat recharge from surrounding rock. If we use incorrect heat capacity or thermal conductivity, long-term temperature forecasts become unreliable. The practical question is, how fast can we extract heat before the produced temperature declines below the useful limit? Thermal breakthrough is one of the most important failure modes in geothermal operations. It occurs when cooler injected water reaches the production well too quickly, reducing the produced fluid temperature and therefore the power or heat output. The arrival time of the cold front depends on injection rate, while spacing, fracture connectivity, sweep area, and thermal recharge from the surrounding rock. In fractured reservoirs, breakthrough can be surprisingly fast if one dominant pathway connects injector and producer. Simulation allows us to test different well patterns and operating strategies before the field loses performance. The goal is not only to move water, it is to sweep heat effectively. Geothermal fluids may exist as liquid water, steam, or a two-phase mixture. In moderate temperature systems, single-phase liquid behavior may dominate, but density and viscosity still change with pressure and temperature. In high-temperature reservoirs, boiling and condensation can occur. Then we must model steam saturation, relative permeability, capillary effects, and enthalpy. The word enthalpy is important because geothermal power output depends not only on temperature, but also on how much usable thermal energy the produced fluid carries. Phase behavior can strongly affect pressure response, production rate, and plant performance. Therefore, property models are not just details, they control the economics. This slide shows why geothermal is a multi-physics system. Thermal processes change fluid properties and rock stress. Hydraulic processes drive circulation and pressure diffusion. Mechanical processes modify fracture aperture and permeability. Chemical processes may cause scaling, mineral precipitation, dissolution, or corrosion. These processes interact. For example, cooling can contract the rock and change stress around fractures. Pressure increase can reduce effective normal stress and potentially reactivate fractures. Mineral scaling can reduce injectivity. So when we say geothermal reservoir simulation, we are not only simulating flow. We are simulating a coupled system where heat, pressure, stress, and chemistry influence each other. Geomechanics is essential for safe geothermal development. Injection changes pore pressure, and pore pressure changes effective stress. Cooling also creates thermal contraction, which can modify the stress field near wells and fractures. These stress changes may improve permeability by opening fractures, but they may also increase induced seismicity risk if faults are critically stressed. This is why EGS and high-rate geothermal projects often use traffic light systems and microseismic monitoring. From a simulation perspective, we need to understand not only where the fluid goes, but also how the stress state evolves. Safe geothermal operation means controlling both pressure and temperature effects. The simulator is useful only if it predicts the right performance indicators. For geothermal systems, key outputs include produced temperature, pressure and injectivity, steam fraction or enthalpy, thermal breakthrough time, power generation or heat delivery, and risk indicators such as induced seismicity or subsidence. These outputs connect physics to decisions. For example, a temperature map helps us understand thermal sweep. A pressure map helps us design safe injection. A risk map helps us decide whether a rate schedule is acceptable. Good geothermal simulation therefore converts complex subsurface physics into clear operational KPIs. Now we enter part 3, building the geothermal reservoir simulator. We have the conceptual model, and we have the physics. The next challenge is implementation. We must convert data, geological interpretation, equations, wells, and operating constraints into a numerical model. This is where reservoir engineering becomes both science and craft. Choices about grid resolution, boundary conditions, well controls, and calibration can strongly affect the forecast. In this part, I will show the workflow used to move from field evidence to predictive simulation. A geothermal simulation workflow usually starts with field data, wells, logs, temperature measurements, pressure tests, seismic interpretation, tracers, and production history. These data are used to build a static model of geometry, facies, faults, permeability, and fractures. Then we add dynamic physics, fluid flow, heat transport, phase behavior, and sometimes geomechanics and geochemistry. After that, we define well controls and operational scenarios. Finally, we calibrate the model against observations and use it to forecast future behavior. The best workflow is iterative. As new monitoring data arrive, the model should be updated rather than treated as fixed. Grid design is one of the most important numerical choices. We need fine resolution where the physics changes quickly around wells, fractures, faults, and thermal fronts. Far from the active zone, the grid can be coarser to reduce computational cost. If the grid is too coarse, the thermal front may become artificially smeared, and breakthrough time may be inaccurate. If the grid is too fine everywhere, the simulation may become too slow for uncertainty analysis or optimization. The rule is simple: put resolution where it matters. Then check grid convergence for pressure response, temperature decline, and power output. Boundary and initial conditions define the model universe. Initial temperature may come from measured well temperatures, geothermal gradient, and thermal anomalies. Initial pressure may follow a hydrostatic profile or include overpressure. Boundaries can be closed, constant pressure, constant temperature, or connected to large regional aquifers. These choices are not small technical details. They control pressure support and thermal recharge. For example, a closed boundary may predict faster pressure buildup, while an open boundary may allow more pressure dissipation. A realistic geothermal model must therefore justify its boundary assumptions using geology, hydrology, and field evidence. When wells are added, the simulator becomes a decision tool. Injection wells can be controlled by rate, bottom hole pressure, injection temperature, or fluid chemistry. Production wells can be controlled by bottom hole pressure, enthalpy target, maximum drawdown, or separator pressure. These controls determine the operating strategy. For example, a high injection rate may increase energy extraction but also raise pressure and induce seismicity risk. A lower injection temperature may improve heat recovery but accelerate thermal stress changes. The simulator allows us to compare strategies and choose a schedule that balances energy, safety, and long-term sustainability. History matching is where the model learns from the field. We adjust uncertain parameters such as permeability, fracture aperture, storativity, boundary support, and heat recharge until the model reproduces observed pressure, temperature, enthalpy, and tracer behavior. However, we should avoid believing in one perfect model. Many different parameter combinations may match the same data. This is why ensemble-based calibration is more honest. Instead of one deterministic answer, we keep a family of plausible models and use them to forecast uncertainty. In geothermal projects, this is critical because decisions must be robust under uncertainty. A geothermal reservoir has many uncertainties. Permeability may vary by orders of magnitude. Fracture networks may be only partially observed. Boundary support and recharge may be uncertain. Thermal conductivity, heat capacity, and fluid properties also vary. Because of these uncertainties, one reservoir can produce many plausible futures. The simulator should not only give a single temperature curve, it should give a range: optimistic, expected, and conservative outcomes. This helps operators design robust strategies. For example, if most uncertainty realizations show early thermal breakthrough, the well pattern or operating rate should be changed before field investment. Monitoring closes the loop between model and reality. Downhole pressure and temperature gauges show how the reservoir responds. Fiber optic sensing can provide distributed temperature information. Tracer tests reveal connectivity, residence time, and possible short-circuit pathways. Microseismic monitoring shows fracture activation and stress response. Geochemical monitoring can detect scaling or water-rock interaction. These data are valuable only if we use them to update the model. This is the idea of data assimilation. The simulator should evolve with the field, becoming more accurate as observations accumulate. Now we enter Part 4, Digital Twins and AI-Assisted Geothermal Simulation. Traditional simulation can be accurate, but it may be too slow for real-time decision-making, uncertainty analysis, or optimization over many scenarios. AI can help by learning fast surrogate models from high-fidelity simulations and monitoring data. But for geothermal systems, purely data-driven AI is usually not enough because field data are limited and the physics is complex. The future is physics-informed AI, models that combine data, simulation, and physical constraints to support fast and reliable decisions. AI-assisted geothermal modeling can support several tasks. Surrogate models can rapidly predict pressure, temperature, power output, or risk from many simulation scenarios. Data assimilation models can update hidden states and uncertain parameters using streaming monitoring data. Pattern recognition models can detect early warning signals for thermal breakthrough or injectivity decline. Optimization algorithms can search for safer injection and production schedules. However, the key message is this: AI should not replace physics. AI should accelerate physics, learn from data, and respect physical constraints. In geothermal reservoirs, interpretability and reliability are just as important as prediction speed. A geothermal digital twin connects the field system, the physics simulator, the AI model, the uncertainty engine, and the decision dashboard. The field provides real-time or periodic monitoring data. The physics simulator represents flow, heat, stress, and chemistry. The AI component accelerates prediction and identifies patterns. The uncertainty engine tells us how confident we are. The dashboard translates results into operational decisions: adjust rate, change pressure limit, modify reinjection temperature, or trigger a safety protocol. A true digital twin is not just a beautiful visualization. It is a living decision support system. Operational optimization asks a simple question with a complex answer. How can we maximize thermal output while respecting safety and sustainability constraints? The objective may be to maximize cumulative thermal power or economic value. But we must constrain pressure, produce temperature decline, induced seismicity risk, chemical scaling, and facility limits. This is why geothermal optimization is not only about producing more. It is about producing responsibly. A good optimization framework searches for rate and pressure schedules that maintain useful heat, avoid early breakthrough, and keep risk below acceptable thresholds. Let us consider a district heating reservoir. The goal is to deliver stable heat to buildings over many years, especially during winter demand peaks. The key forecast is produce temperature decline under seasonal operation. The simulator must predict whether the reservoir can maintain supply temperature, how much reinjection cooling affects future production, and whether additional wells are needed. For district heating, economics may depend on reliability more than maximum power. Therefore, a conservative reservoir management strategy is often valuable. Simulation helps design a heat system that is not only technically possible, but dependable for communities. In enhanced geothermal systems, the rock is hot, but natural permeability may be insufficient. Controlled injection is used to create or reopen fractures and establish a connected flow network. This is promising, but it requires careful design. Too little stimulation gives poor circulation. Too much pressure may increase seismic risk. The simulator must connect hydraulic stimulation, fracture permeability, heat extraction, and geomechanical response. EGS is therefore a frontier problem in geothermal reservoir engineering. It combines drilling, stimulation, monitoring, risk management, and multi-physics simulation in one integrated workflow. Every geothermal project must manage risk. Thermal breakthrough can reduce power output. Induced seismicity can affect public acceptance and safety. Scaling and corrosion can damage wells and surface facilities. Injectivity decline can reduce circulation. Subsidence or ground deformation may occur in some settings. Simulation helps by converting these risks into maps, thresholds, and early warning indicators. Instead of reacting after a problem appears, we can test scenarios in advance. We can ask, which operating strategy gives the best heat recovery while keeping pressure, temperature, and stress changes within safe limits? Geothermal energy is renewable only if the reservoir is managed as a renewable asset. Thermal sustainability means we should not extract heat faster than effective recharge and sweep can support. Water sustainability means reinjection, makeup water, and chemistry must be managed carefully. Mechanical sustainability means pressure and stress changes should remain within safe limits. Social sustainability means the project must be transparent, safe, and beneficial to local communities. This is where reservoir simulation supports responsible energy transition. It helps us move from the question, can we produce heat, to the better question, can we produce heat safely for decades? Geothermal reservoir research is moving quickly. Superhot rock systems may offer much higher power density, but they require extreme drilling, materials, and reservoir control technologies. Closed-loop systems reduce some fluid rock uncertainties, but introduce heat exchanger design challenges. Hybrid geothermal systems may integrate with hydrogen production, district heating, carbon storage, or industrial heat supply. AI and digital twins will make reservoir management faster and more adaptive. The future of geothermal is not one technology. It is a portfolio of subsurface heat solutions, guided by simulation, monitoring, and risk-aware operations. Let us summarize the 5-step geothermal simulator mindset. Step 1. Define the heat engine, including heat source, fluid pathway, and wells. Step 2. Translate the system into equations for mass, flow, energy, mechanics, and chemistry. Step 3. Discretize the system with a grid that resolves the important physics. Step 4. Calibrate the model using pressure, temperature, production, tracer, and monitoring data. Step 5. Use the model for decisions under uncertainty. If you remember only one message from this lecture, remember this. Geothermal simulation is the science of turning invisible subsurface processes into visible, testable decisions. Before we close, I want to ask 2 questions for discussion. First, which factor do you think controls thermal breakthrough most strongly? Wall spacing, permeability, or injection rate? My answer is that all 3 interact, but permeability architecture often determines the pathway. Second, should geothermal AI models be purely data-driven or physics-informed? My view is that physics-informed AI is the safer and more scientific direction, especially when field data are limited. Please share your thoughts in the comments, because these questions are exactly where geothermal reservoir engineering becomes exciting.